Welcome back to my rubber heart. Today we are revisiting natural rubber and how we fortify it against a common environmental enemy, ozone. This starts with the chemistry and the vulnerability of natural rubber and then builds into a full arsenal of protection strategies. Natural rubber, made of cis-1,4-polyisoprene, is rich in double bonds, exactly the places where ozone can attack. Unlike other rubbers that only have double bonds occasionally, NR has them in almost every repeat unit. So even very low ozone concentrations will start to cleave those bonds right on the surface. That cleavage forms ozonides, which break apart into ketones and aldehydes, weakening the rubber and creating cracks perpendicular to the strain axis. Over time, those tiny cracks turn into material failure. The classic ozone cracking you see on old hoses, seals, and tire sidewalls. To defend NR, we use a multi-layered approach. We begin with wax barrier systems. These are often the first line of defense. You might have noticed a fine waxy sheen on fresh tires. That's migrating wax, a mix of paraffinic or microcrystalline waxes that slowly blooms to the surface and forms a film to physically block ozone. But here's the catch. This layer only works while the wax remains solid. If the rubber part is used across a wide temperature range, a low melt wax might soften and flow away at high temperature, or crack on the surface during expansion and contraction. That is why compounds often contain wax blends, different waxes with different melting points, so that even if one allele of the film softens, another component remains intact and protective. In dynamic applications, say a rotating seal or flexing hose, the wax layer often fractures at the surface, losing its protective ability. It just can't hold up like a chemical barrier under movement. That is where chemical antiozonants come in, typically IPPD and 6-PPD. These compounds start beneath the surface, migrate outward, and react preferentially with ozone. They form sacrificial radical intermediates and eventually ketones, neutralizing the attack before it reaches the rubber chains. It's a self-replenishing shield, one that recharges itself as ozone is consumed and more antiozonant migrates to the surface. So as long as there is a reservoir inside, NR stays protected. But we don't stop there. We layer in antioxidants like hindered phenols or aminic stabilizers. These compounds work in synergy with antiozonants. When the antiozonant reacts with ozone, it forms radical fragments. Left unchecked, those radicals could trigger oxidative breakdown deeper in the rubber. Antioxidants step in here, scavenging those radicals before they initiate chain scission. They don't intercept ozone directly, but they prevent the damage it starts from continuing. Without antioxidants, ozone protection would stall mid-sentence, leaving NR weaker than before. Together, waxes slow down ozone penetration on the surface, antiozonants intercept and neutralize it chemically, and antioxidants mop up the residual radicals to protect the interior. Each layer fills a gap that the others can't cover. In real-world applications, think automotive hose, weather seals, outdoor conveyors, we rely not on a single ingredient, but on this teamwork. Waxes form the initial barrier, antiozonants build the chemical defenses, and antioxidants secure the structural integrity of the polymer network. That is the art and science of designing ozone-resistant rubber. Understanding that each ingredient has a role, whether physical or chemical, and that they must complete each other to create protection that lasts across temperature swings and mechanical stress. Thanks for tuning into my rubber heart. If you'd like to explore exactly which wax blends work best for a heavy-duty hose, or dive into the migration rates of 6-PPD and antioxidants, just say the word. Stay resilient and see you next time.